All right, verifying trigonometric identities. Okay, so our main goal is to verify identities, and a lot of these identities are just going to be verified by using the fundamental identities, which you can see here in this box. So these should be familiar to you already. First, let's go over the reciprocal identities. So depending on the definition of the 6 trig functions, you could verify these identities in different ways. So for example, if we're on the unit circle, then we know sine is the y coordinate of the unit circle, and then of course cosecant is just 1 over y. So then it makes sense that 1 over y is just y, and so you get sine of x, right? So likewise, cosine of x we know is the x coordinate on the unit circle, and so 1 over x gives you just x. All right, but the reciprocal of cosine is 1 over secant of x, right? Tangent, the reciprocal identity is tangent of x is equal to 1 over cotangent. Cosecant of x is equal to 1 over sine of x. Secant of x is 1 over cosecant of x, and cotangent of x is 1 over tangent of x. Those are the reciprocal identities. And then likewise, the quotient identities, we know tangent is just the ratio of y over x if you're thinking the unit circle, and therefore, well, sine is just x, or sine is just y, and cosine is just x. Could be confusing of the fact that I'm using x as the angle argument, but just ignore that, replace it with theta, and you have the same thing there. And then cotangent is just like the y coordinate over the x coordinate, so we know that's cosine over sine. And then if you're on the unit circle, we know x squared plus y squared equals 1, and that's where you get the main Pythagorean identity. And then if you divide, say, this left-hand side of the sine squared and cosine squared by, say, sine or cosine, you get the respective other identity by simplifying or rewriting it, because you know how the reciprocal functions or reciprocal identities behave. Okay, and then even and odd identities. All right, so let's use let's verify identities. What does that mean? Well, the fundamental of these are useful to establish the relationships among trigonometric functions. To verify an identity, we show one side of the identity can be simplified so that it is identical to the other side. Verify the identity secant of x times cotangent of x equals cosecant of x. I tend to work with the left-hand side or whatever side looks a little bit more complicated. It doesn't always work, but it can. Sometimes these things are just trial and error, but I'm going to take the left-hand side, and we'll take secant of x and cotangent of x. And then we're going to rewrite secant of x using, say, rewriting secant of x and cotangent of x in terms of sines and cosines using the respective quotient identity or reciprocal identity. So we know secant is 1 over sine of x, or excuse me, cosine of x. And then cotangent we know is cosine of x over sine of x. And there you can see that the cosine of x will cancel, and we're left with 1 over sine of x, which gives us just, well, 1 over sine of x, using the reciprocal identity, we know that's just cosecant of x. And so that's the right-hand side, which is what we wanted to show. So that identity is verified. Okay, let's try the next one here. We have sine of x, tangent of x, plus cosine of x equals secant of x. All right, so I'm going to go ahead and start with the left-hand side again here. So sine of x times tangent of x plus cosine of x. All right, well, tangent of x is sine over cosine. So we could write this as sine of x, and then tangent of x is sine of x over cosine of x. So we get that. And then sine of x times sine of x over cosine of x becomes sine squared of x over cosine of x plus cosine of x. All right, well, we could think of cosine of x over 1 here, and then multiply top and bottom by cosine of x so that we could find a common denominator, which would give us sine squared of x over cosine of x plus cosine of x over cosine of x. Sorry, cosine squared of x over cosine of x. And then, of course, we have the same denominator, so we can combine the numerators as sine squared of x plus cosine squared of x all over cosine of x. While using the Pythagorean identity, we know sine squared of x plus cosine squared of x is 1. So we have 1 over cosine of x. And then now 1 over cosine of x is just secant of x, because that's what do you call a reciprocal identity. So that is secant of x, which is the right hand side. And that's what we wanted to show. All right, let's try the next example here. Verify the identity. Cosine of x minus cosine of x times sine squared of x equals cosine cube of x. Once again, I'm going to go ahead and work with the left-hand side here. And then I'm going to use the Pythagorean identity, because we know the Pythagorean identity says sine squared of x plus cosine squared of x equals 1. But I'm going to manipulate it. Meaning I'm going to subtract cosine squared of x on both sides, so that it says that we have sine squared of x equals 1 minus cosine squared of x. And then I'm going to replace that sine squared in our identity with 1 minus cosine squared of x. So we have cosine of x minus cosine of x times 1 minus cosine squared of x. And doing so, well, we can distribute there, so we get minus cosine of x, and then a negative cosine of x times negative cosine squared of x becomes negative, or negative makes it positive, but then cosine of x times cosine squared of x becomes cosine cube of x. And well, you can see that these terms cancel, giving us 0, which leaves us with just cosine cube of x, which is the right hand side. And we have verified that identity. All right, let's try another one. Here we have 1 plus cosine of theta, which equals secant of theta plus tangent of theta. Either side would be just as good to start with, and just to change it up a little, let me go ahead and use the right hand side. So we'll take secant of theta plus tangent of theta. And I'm going to rewrite these functions using the reciprocal and quotient identity, meaning changing to cosine and sines. So we have 1 over cosine of theta plus sine of theta over cosine of theta. All right, now since we have a common denominator, we can combine the numerator to get 1 plus sine of theta all over cosine of theta. And that's exactly the left-hand side. And so we are done there. Likewise, you could have probably split the fraction if you start at the left-hand side and end up exactly with the right-hand side as well, using the reciprocal identity. Just rewrite the argument backwards. All right, so we're asked to verify the identity again here. So we have cosine of x, so all over 1 plus sine of x, plus 1 plus sine of x over cosine of x equals to secant of x. So I'm going to definitely start with the left-hand side here. And to do so here, I'm going to multiply this first term here by cosine of x, so I could get a common denominator. And the second fraction here by 1 plus sine of x, top and bottom there. So this way we have a common denominator. All right, so I'll get cosine of x times cosine of x, which gives me cosine squared x all over cosine of x times parentheses 1 plus sine of x. Okay. Then I have plus, and I'm going to go ahead and distribute here. 1 times 1, so that gives me 1, and then 1 plus 1 times sine of x, plus 1 times sine of x again, which gives us 2 sine of x, and then plus sine times sine, so that's sine squared of x, all over cosine of x times 1 plus sine of x. All right, so now combining this as one big fraction, I'm going to have cosine squared of x plus sine squared of x from this guy over here, and I'm left with plus 1 plus 2 sine of x all over cosine of x times 1 plus sine of x. All right, well, we know that's going to equal 1 because of the Pythagorean identity there. So we're left with 2 plus 2 sine of x all over cosine of x times 1 plus sine of x. All right, and so we can see there's a 2 in common in the numerator there, so let's factor that out, and that leaves us with 1 plus sine of x all over cosine of x times 1 plus sine of x. And we can see that 1 plus sine of x will cancel on top and bottom there, leaving us with 2 over cosine of x, which is the same thing as 2 times 1 over cosine of x. And so using the reciprocal identity there, we have 2 times secant of x, which is the right-hand side. And we have verified that identity. All right, let's try another one. Verify the identity that sine of x over 1 plus cosine of x equals 1 minus cosine of x over sine of x. This one here is more of a, what I like to call a little trick. Once you see it, it's helpful to do this. So whenever you see a 1 plus cosine or 1 minus cosine, it's sometimes helpful to multiply by what's known as something like a conjugate, meaning the opposite, basically change the sign in the middle. So I'm going to go ahead and use this what you call left-hand side. So I'm going to have sine of x over 1 plus cosine of x, and then, like I said, we're going to multiply by the conjugate of the denominator, which would be 1 minus cosine of x and 1 minus cosine of x. And the reason is because when you multiply conjugates, so like a minus b times a plus b, you get a squared minus b squared when you follow it out. And this usually gives us some nice properties, this particular with sines and cosine. And so doing so, what does that give us? Let's see. We have a sine of x times 1 minus cosine of x. And then on the bottom here, we would have 1 times 1, and then 1 times negative cosine of x, and then another 1 times cosine of x, and those terms would cancel out, leaving us with minus cosine squared of x. And earlier we showed that the Pythagorean identity is equivalent of 1 minus cosine squared of x is the same thing as sine squared of x, where we did that manipulation, and there was it at? Right here. And so we could use that again to rewrite the denominator as simply as sine squared of x. So on the top we still have sine of x, and then 1 minus cosine of x all over sine squared of x. And we can see we're going to cancel one factor of x, leave us with sine of x. And so what is that? 1 minus cosine of x all over sine of x, which is exactly what we wanted to show. So let's check. All right, one more to go here. So let's verify the identity. Tangent of x minus sine of negative x all over 1 plus cosine of x equals tangent of x. Once again, let's use that left-hand side. It looks like it has more to work with there. So tangent of x minus sine of negative x all over 1 plus cosine of x. Alrighty, well, sine is what we call an an odd function, which means we would have tangent of x on top there, but minus, well, times a negative sine of x, because the negative will pop out. And so what does that give us? That gives us basically tangent of x plus sine of x all over 1 plus cosine of x. And the route I'm going to take here is just I'm going to rewrite tangent as sine over cosine using the quotient identity plus sine of x over all over 1 plus cosine of x. All right, and now I'm going to combine my numerator. So I'm going to combine that as sine of x over cosine of x. But then finding a common denominator, I'm going to add and multiply top and bottom here by cosine of x, which would give me sine x cosine of x all over cosine of x. So this way I get sine of x plus sine of x. By the way, this is all over, this is all over 1 plus cosine of x. Can't just drop that. That's still there. Okay, so we're left with sine of x plus sine of x cosine of x all over cosine of x. And this is all over 1 plus cosine of x. All right, so I'm going to think of this as a fraction here. So then I'm left with the first fraction here. And then notice that the numerator here has a sine of x in common there, so I'm going to factor that out, which leaves me behind 1 plus cosine of x all over cosine of x, but then I'm dividing by 1 plus cosine of x, so I'm going to flip that over and multiply by the reciprocal of the denominator there, so 1 over 1 plus cosine of x, and you can see then that's exactly what I want because that would cancel. Leaving me with sine of x over cosine of x, which is just tangent of x, using the quotient identity, which is the right-hand side, and that's what we wanted to show. And so we have verified that identity, and that's it for this video.